Hello everyone, this is Professor Keen. In my previous lecture, I began discussing the technique of dimensional analysis, and we spent some time talking about the dimension of various physical quantities like length and time, mass, force, pressure, acceleration, and velocity. So that hopefully gave you a little bit of practice in understanding what we mean by the dimension of a quantity. The idea is that the dimension of a quantity expresses something that is more general than the particular units you are using. So, for example, when you were talking about length, you could be measuring length in meters, or in feet, or in inches, or in centimeters, or in furlongs, or whatever unit you want, and yet all of those have the dimension of length. Likewise with time, one can measure time in days, or hours, or weeks, or seconds, or milliseconds, or heartbeats, but all of those have the dimension of time. So now, how can we use this technique in order to find, for example, the frequency of vibration of a pendulum? So let me cut away from my webcam and show you my sketchbook, and I'll show how one does this procedure. So here's the question that we're asking. How can we use dimensional analysis to determine a formula for the frequency, or alternatively the period, the frequency of a pendulum? That's the question we're asking. So let me draw a picture here. So here's the ceiling, and we've got a string hanging down, and we've got a mass, and so here's the mass. The string has some length like this, and of course gravity, the gravitational force, is pulling it downward in that direction, and that's why when you release it, it swings back and forth. So let me write out here, L is the length of the string, M is the mass of the pendulum bob, and G here is the acceleration of gravity. And as I think I mentioned in my previous lecture, the technique of dimensional analysis essentially consists of identifying quantities that you think may have some effect on the frequency of this vibrating system, and then finding an appropriate combination of those variables that gives you the correct dimensions of frequency. So our first step then is to say, well, we've already partially done it here. We want to find a formula for the frequency of this swinging pendulum, right? And that frequency we suspect is going to be a function of perhaps the length of the pendulum. Maybe it depends on the mass. I know Galileo told us it doesn't depend on the mass, but let's suppose we're more naive and we said it may depend on the mass. It also probably depends on the strength of gravity, and those are presumably the quantities that it depends upon. You know, it shouldn't reasonably depend upon the color of the bob or, you know, the time of day. Those seem to be unreasonable, although it's conceivable that those could have an effect. But let's start with these quantities and say, how can we find a combination of these that gives us the dimension of frequency? So let's identify the dimension of these various quantities. Okay, so I'm going to use a notation that's common in physics and say, well, the length of the string, what is the dimension of that? The square brackets mean the dimension of the length is just, well, using the table we came up with in our last lecture, it's just the length. What about the dimension of the mass of the bob? Well, that's just the dimension mass. What about the dimension of gravitational acceleration? Well, looking back at the table from last time, it has the units of length over time squared. Remember, in a particular system of units, it might be meters per second squared, but abstracting from the units, it is a measure of length over time squared. And what about frequency? Frequency has the units, or the dimensions of 1 over time, right? So now what we want to do is we want to find the correct formula for frequency. I'm going through this kind of quickly, but you'll get the hang of this. We'll do a couple of examples. So frequency should be proportional to some combination of these variables. And we want to know what combination we can form that has the correct dimension. So the dimension of frequency is, like we said here, 1 over time. And so whatever we put on the right side of this formula has to have the same dimension as 1 over time. Well, what variables here have the dimension of time in them? Well, g does. It has a dimension of time here, but it has dimension of time squared. So we would have to perhaps have a square root of g here. That way the square root of g is going to have the dimensions of the square root of length over time. Do you see that? Because the square root of length and then the square root of time squared is time. So if we put a square root of g in the numerator, we will get a dimension of the square root of length over time. Now the left-hand side has units of 1 over time, or dimensions of 1 over time. Here we have the dimensions of 1 over time times the square root of length. So somehow we need to get rid of this square root of length. How do we do that? Well, let's look back at these variables. What has the dimensions of length? Well, the length of the pendulum does. But we want to get rid of the square root of length, so we'll probably need to use the square root of the length of the pendulum. That way, that will introduce a dimension of 1 over the square root of length. Look at that. Now, if we say the frequency goes as the square root of g over the square root of L, that quantity, those cancel out, is proportional to the dimensions inverse time, which is precisely what we want for frequency. Therefore, we have found a function of those variables that has the correct dimensions, okay? And since the frequency we've just found is proportional to the square root of g over the square root of L, that gives us the right dimensions. We could also find the period t. Period goes as 1 over frequency, so that's the square root of the length of the pendulum over the square root of g. Okay. Notice that we don't know whether it's equal or not. We could still have some other factors in here, like some numbers that don't have any dimension, and it wouldn't screw up our dimensional analysis. But you might remember that the formula for the period of the pendulum is 2 pi times the square root of L over g. So these two formulas are consistent with each other. One is an equation and one is a simple proportion. And for dimensional analysis, all we can really do is figure out how the period of the pendulum depends on quantities like length and the acceleration of gravity. So this is a very nice technique that gets you almost to the formula, but not quite. Okay, let's do one other example before we quit. So let us find the period of a vibrating string. So this will be example 2, and then we'll stop after that. So what about a vibrating string? Okay, remember this is the monochord example that Galileo had talked about. I'll draw a side view where we have a string that is tied, placed over two, tied right here, placed over a couple of, I don't know what you call those, and then a pulley right here, and the string is stretched over this pulley, and then you put a weight right here, and this applies some tension. So there's a tension that is being applied to this. The string has some length, and of course it has a mass per unit length, mu. And again, I'll use an orange pen here. We want to find the frequency of vibration, and we suspect that the frequency of vibration is going to depend on, let's call this little l, on the length of the string, the tension, and for reasons that will become obvious in a moment, let's call tension the Greek letter tau. So that way we won't confuse it with the dimension of time. Okay, so length, tau, and the tension, and the mass per unit length, mu. Okay, it's going to be some function of these variables. Let's find out what that function is. Well, what are the dimensions of the length of the string? Well, that has dimensions of length. What about the dimensions of the tension in the string? Well, you might want to look back at our previous table. It has units of mass, or dimensions of mass, times length over time squared. What about the dimensions of mu, or mass per unit length? Well, that has dimensions of mass over length. And once again, the dimensions of frequency are going to be 1 over time. Okay, so let's look at the formula. Our formula is going to be the frequency is proportional to some combination of these variables. What combination of those variables will give us the correct dimension? Well, let's do this dimensional analysis. Okay, on this side of the formula, frequency, that has units of 1 over time. So whatever appears on this side of the formula has to have dimensions of 1 over time as well. Well, what variables in here have dimension of time? Well, the tension does. That's the only one that has dimensions of time. But notice it goes as 1 over time squared. So if we put a square root of tension in the numerator, that will give us a square root of mass and a square root of length and a time in the denominator. Okay? Now, we can't have these appearing on the right-hand side because that would give us the wrong dimension on the left-hand side. So we need to use some other combination of variables that can cancel these out. Okay? Well, we could use, we see this one has mass over length. What we could do is we could use a square root of mu. So let's put a square root of mass per unit length here, and that would introduce a square root of mass in the denominator and a square root of length in the numerator. Okay, well that solved one of our problems, but it created another one. So notice that cancels out, the square root of masses cancel out, but now we've got to get rid of 2 square roots of L, or just a factor of L. Well, we can do that because we still have one more variable, the length, and so if we put a length in the denominator, that puts a factor of length in the denominator here, and that is going to cancel both of these, and so we have dimensions of 1 over time. Voila! Don't you see that? Now we have a formula that relates the frequency of vibration of the string to these quantities, square root of tension over the square root of mass per unit length times a length. And that is precisely the formula that we came up with in our previous lecture for the frequency of vibration of a string. So here once again, we can see how the technique of dimensional analysis is a very nice technique for figuring out things like the frequency of vibration of systems that have natural vibrational frequencies. Let me just point you to a couple of other problems. I think I assigned some homework problems. There's another one, example 3, where you're trying to find the frequency of vibration of a mass spring system. So imagine a spring with a mass hanging on the end, and you pull it down and it springs up and down. What is the vibrational frequency of that system? You can do other more exotic ones, like if you have the sun right here and the earth right here and the earth going around the sun, it takes some time to go around, and can you figure out a formula for the time of orbit of the earth around the sun using dimensional analysis? And the answer is yes, you can. So I will stop there, and we will move on next time to talking about chapter 6 on beam breaking.